hybridization. Different orbitals mix together to form same orbitals. How different? They have different energy, different size, and different shape. The same orbital formed have same energy, same size, and same shape. This process is known as hybridization. Types of hybridization: sp3, sp2, sp, dsp2, dsp3, and d2sp3 are various modes of hybridization in which s and p orbitals mix together, or d, s, and p orbital mix together. First type, sp3 hybridization, in which one s, that is of low energy, and three p orbitals, they are of high energy, mix together to produce four new orbitals. They are hybrid orbital. Each orbital is now termed as sp3 orbital. sp3 orbitals geometry. Now they will show a tetrahedral arrangement on the hybrid atom. These orbitals are sp3 orbitals arranged in a tetrahedral geometry having an angle of 109.5. Remember this for sp3 hybrid orbitals. This angle varies when there are lone pairs in the orbitals. So the electronic geometry over here is tetrahedral and the angle remains 109.5. Each sp3 orbital has 25% of s character and 75% of p character because they mix in 1:3. sp2 hybridization. In this hybridization, 1s and 2p orbitals combine, giving us 3 hybrid orbitals. Each orbital is sp2, sp2, and sp2, and one unhybrid orbitals p. Now this unhybrid orbital has its own energy, size, and shape, while the energy, size, and shape of the hybrid orbital is same. sp2 orbitals geometry, they give us triangular planar geometry, in which the hybrid orbitals are in one plane, having an angle of 120 degree between them, while the unhybrid p orbital remains perpendicular to the plane of the triangle. So this is the geometry of sp2 orbitals, that is known as triangular planar geometry with an angle of 120 degree. Each orbital has 33.3% s character and 67.7% p character because they combine in the ratio of 1 of s ratio 2 of p. So due to this ratio, they have these percent character of s and p orbitals. sp hybridization. In this hybridization, 1s and 1p orbital mix together, giving us 2 hybrid orbital. Each orbital is sp labeled or termed, while 2 unhybrid p orbitals. sp geometry. The 2 sp orbital are at maximum distance from each other, giving us an angle of 180 degree with linear geometry, while the 2 unhybrid orbital py and pz remain in their axis perpendicular to the hybrid orbitals. Each sp orbital has 50% s character and 50% p character because they mixed in 1:1 ratio. Now let's see the sp3 hybrid orbitals bonding, at what type of bond they can form. Remember, all hybrid orbitals form only sigma bonds. In methane, carbon uses all its sp3 hybrid orbital forming sigma bonds with hydrogens. In ammonia, nitrogen uses all the sp3 hybrid orbitals forming sigma bonds with 3 hydrogen, while its lone pair reside in the 4th sp3 hybrid orbital. While in oxygen, 2 sigma bonds are formed with 2 hydrogen atoms, and the remaining 2 orbitals, they are sp3 orbitals, are occupied by the 2 lone pairs. This is why the angle decreases in these molecules. In methane, it is 109.5. In NH3, due to the greater repulsion of the lone pair, the angle decreases up to 107.5 degree. While in H2O, because of the 2 lone pair, more repulsion, the angle decreases up to 104.5 degree. And again, the electronic geometry is tetrahedral, but the shape of molecule are different. Methane is tetrahedral, ammonia is pyramidal, and water is angular. sp2 bonding. First look at the example of boron trifluoride, in which all the 3 hybrid orbitals are involved in sigma bonding with 3 fluorine, and the unhybrid p orbital remains empty in this case. In case of C2H4 ethene, the 2 carbon are sp2 hybrid, having 3 sp2 hybrid orbitals, and they use it in sigma bonding, carbon to carbon, carbon to hydrogen, carbon to hydrogen. while the not empty here, the unhybrid p orbital having one electron each in each carbon, they form a pi bond by parallel overlap. To understand bonding in sp hybrid atoms, let's see an example of carbon dioxide, in which carbon is sp hybrid having two sp hybrid orbital and two p unhybrid orbitals, while each oxygen is sp2 hybrid having three sp2 hybrid orbital and one unhybrid p orbital. The same is for the second oxygen. Now, the sp hybrid orbital of carbon and sp2 hybrid orbital of oxygen, they are on linear overlap, producing carbon sigma bond oxygen, while the lone pair of oxygen resides in the two sp2 hybrid orbitals. These are those lone pairs. The second oxygen also form a sigma bond with sp hybrid orbital of carbon by overlapping sp2 sp bond, sigma bond, and this is that oxygen. And the same for the second oxygen, the lone pair reside in the sp2 hybrid orbitals. Now, the unhybrid p orbital of carbon and that of oxygen form pi bond by parallel overlapping. We got a pi bond over here to the right oxygen, and again, the unhybrid second p orbital of carbon and unhybrid p orbital of oxygen, they have linear overlap, and the next pi bond is formed between carbon and oxygen. And the geometry of carbon dioxide is linear with 180 degree. So in this case, the pi bonds are formed by pp overlap, all the two pi bonds, while the sigma bonds are formed sp orbital of carbon and sp2 orbital of oxygen. The sigma bonds are formed by this overlap, and both the pi bonds are formed by pp overlap. So this was bonding in sp hybridization.